Unit 5, Kinetics, Chem II, Mrs. Peachy, Lee Summit High School. Kinetics can also be referred to as reaction rates. If you could look now in your notes packet that you were handed to at the beginning of the hour to page 2. Meaning of reaction rates. A couple things I want to point out on the slide here. Please read the definition. I'm not going to read it out loud to you. So here you have a generic reaction where you have two reactants, A and B, forming reactants C and D. Remember, this is a generic way to write a balanced reaction. These letters in front, the lowercase letters, represent the coefficients or moles needed to write the reaction. Notice that it says how the concentration of reactant or product changes with time. Molarity is concentration. I wanted to remind you that molarity is moles over liters. Molarity comes with a big M for its unit. So you could have a number with a big M at the end of it. And if you have a number with a capital M at the end of it, that would indicate to you that that number represents molarity, which is moles over liters. We could also represent molarity by square brackets. So here you have a reaction where you can write the rate. The rate is equal to the change in concentration over, let me just fix this really quick. I don't like how that's laid out. That's a little better. Let's try that again. So then rate is equal to the change in concentration over the moles of A divided by change in time equal the change in concentration of B over the moles of B times change in time equal to the change in concentration of product C with the moles of product C over change in time, and the change in concentration of D divided by the moles of D times change in time. Notice that you have negative sign here and here. That negative symbol is needed for the reaction because we are decreasing the reactants over time. Of course, the reactants will decrease as the products increase. So as I use up reactants, I form products. Example 1. So here we have a reaction, N2O5 gas going to 2NO2 gas plus 1/2 O2 gas. In the time it takes 1 mole of N2O5 to decompose, 2 moles of NO2 and 1/2 moles of O2 gas will form. Write the reaction rate for this decomposition. So the way we do this then is we're going to say rate equals negative the change in the concentration of N2O5 over change in time equals the change in the concentration of NO2 over 2 times the change in time equals the change in the concentration of O2 over 1/2 the change in time. Notice that a couple things. I have made this negative because it's a reactant. These both are positive or not have a sign because they are products. Notice that there is not anything here because there's 1 mole of N2O5. There's a 2 here because there's 2 moles of NO2. And there's a 1/2 here, that's 1/2, because there's a 1/2 mole of O2. One concept we'll look at here is reaction rate and concentration. Reaction rate is ordinarily related to the reactant concentration, i.e. the higher the concentration of the starting materials, the more rapid the reaction. Reactions occur as a result of collisions between reactant molecules. The higher the concentration of the molecules, the greater the number of collisions. The greater number of collisions, the faster the reaction. As the reactants are consumed, their concentration goes down, collisions become less frequent, and the reaction rate decreases. Learning how to write a rate expression. A rate expression has the form rate equals K concentration to N, or you can use X, Y, Z. Any letter can be used here in the place of an N, but that superscript or that exponent represents the order of that reactant. Because we're talking about reaction rates, we will be using reactants only, not products in our expressions. So when I put something in square brackets like I have A here, it's the concentration of the reactant or reactants. If there's more than one and they are ordered, then you will write them in your expression. You'll see how that comes here in just a moment. And then K is called the rate constant. K is called the rate constant. So if I had a reaction that was A plus B plus C, forming some kind of products, I would write rate equals K, concentration of A to X. We're going to be able to use different methods to figure out what the order is. Sort of the whole purpose of this part of the unit. Concentration of B raised to a power Y. Concentration of C raised to the order N. So I could use the word power, but a chemist would use the word order. So my orders are X, Y, and Z. Those will become numbers. Generally speaking, 1 through 3. Pardon me, generally speaking, 0 through 3. Generally speaking, 0 through 3. That will be taught to you here to come. Please read the following slide. Okay, some important things to mention now that you've read it. As I mentioned before, we'll only be using the concentration of the reactants, not the products will appear in the rate expression. What is extremely important for you to note is that the power to which a concentration reactant is raised is called the order of the reaction. So that's where this would be X order, Y order, Z order, N order, A, B, C order. Whatever I want to use for my exponent, I would call that the order. Please note, it is not necessarily the same as the coefficient of the reactant. Meaning that if you had a 2 here in front of this A, that doesn't mean this X becomes a 2. You have to calculate, graph, and or find other ways to figure out the order. Again, do not use your coefficients as your orders. Those have to be calculated or obtained from a graph. So we have things that are 0 ordered, 1st ordered, or 2nd ordered. 0 order means that if the concentration of the reactant doubles, the rate remains the same. So if I double my concentration of a reactant, the rate of the reaction does not change. It happens at the same amount of time. 1st order means that if the concentration of the reactant doubles, the rate doubles. So if something is 1st ordered, when I double the concentration, I should expect that the reactant becomes products at double the speed. 2nd order means that if a concentration of the reactant doubles, the rate increases 4 times. So in other words, if I have something that is 2nd order, then I expect the rate to go 4 times faster. Then to get the overall order of reaction, it's the sum of the individual orders of the reactants, or the sum of the exponents. Let me explain further. Example 2. For the reaction A plus B plus C equals D plus C, the rate expression was experimentally determined to be rate equals K sub 1, concentration of A to 2, and concentration of C to a 1. Let's talk about the expression. So we always will write rate equals, yes, you need to write out the word rate, not R. Rate equals K. The subscript 1 here is not extremely necessary. It's really there for when we have a multi-step reaction. We will not have any of those for a while. Towards the end of the unit, we will start to see those. But for now, you could have just put K or K1. Either way is fine. Then you have square brackets. Remember that square brackets means concentration, moles over liters. So the concentration of A to the 2, exponent of 2, and concentration of C to the exponent of 1. Why 1? Because there's nothing there, so we assume it to be a 1. Question says, what is the order of each of the reactants in the overall order? Let's go through this. So, as we look at this, concentration of A is 2nd order. Concentration of B is 0 order. Remember, anything to the 0 power is 1, so if B is raised to the 0 power, it will disappear. And then a concentration of C is going to be 1st order. Let's talk about how that worked. This 2 of A comes there. There's no B. And remember, there's a 1 here. Even if you don't write it, that's how we get 1st order. Then overall, just add them up. 3rd order. Okay, on to example 3. Here we have 2x gas plus y gas equals products. What is it? That is 1st order in both X and Y. And I don't know why my Y is off my screen, but let's fix that. I probably have it covered up. All right, sorry about that. Now that's fixed. Okay, so it tells us in this thing, remember, in order to determine the order, it has to be graphically done or experimentally determined. So, or we have to be told. In this case, we're told that both X and Y are 1st order. So every time you want to do a calculation, you must have the rate expression. So let's write that. Rate equals K, X to the 1st, Y to the 1st. Now, I could write 1s in here, but that's not necessary. We know that if there's no superscript or exponent value, then it's 1. So let's go through how to do some calculations with this. Now, I realize that there's a 2 in front of here. But remember, this number does not necessarily equal the coefficient that you'd put here. This number here does not equal the coefficient that you'd put there. They might, but that's not how you would figure out the order. You have to be told, or you have to graphically or mathematically determine. It says that both x and y are first order. That's why I don't have any exponents or superscripts there. We assume it to be 1. All right, so we're going to go through these 3. We're going to go through the first 2. You're going to do the second 2 in your notes as part of your assignment. So let's go through A. So A equals rate equals K, X times Y. Now, as always, ladies and gentlemen, I expect you to put numbers, units, and formulas in everywhere. Failure to do this could result in a deduction in points or loss of points totally for an assignment. So let's look at what information we have. We're looking for rate, so I don't have that for A. I'm going to plug in my rate constant, 1.89 liters per mole hours, times my concentration of, remember that concentration is moles over liters, my concentration of Y, square brackets mean, square brackets there, so down here means that you're putting moles over liters in. Okay, so let's go through and let's figure out this answer. We're going to multiply 1.89 times 0.100 times 0.400, and we're going to get 0.0756. And yes, you need to include units in your answers. If you think about this moles would cancel with this moles, this liter cancels with this liter, so what we have left then is moles over liter hours. Sometimes you'll see H for hours, sometimes you'll see HR. Okay, for example 3B, let's remind ourselves, because I paused and switched the screen, rate equals K. X to the first order, Y to the first order. So for 3B, here's how we will proceed. So we have a rate this time, 0.159. Yes, you need to include units. Moles over liters hours equals K, which is 0.884 liters per mole hours times X, which is 0.600. Remember, square brackets means moles over liters. And then we're solving for Y. So what we're going to do is we're going to solve for Y. To do that, notice that anytime I write a rate expression, everything is being multiplied. So to undo multiplication, I have to divide. So I'm going to multiply these two numbers here and then divide them over. I'm going to do this in steps, write down what you need. So the first thing we're going to do is we're going to multiply 0.884 times 0.6. And I get 0.5304. Now when I multiply this, moles is going to cancel with moles because they're on top and bottom. Liters cancel with liters. And I'm going to have inverse hours. Or, as you know, hours is on the bottom. It's going to stay on the bottom. Let me double check my number. 0.884 times 0.6. Okay, I agree with my number. Not doing a good job with sig figs. Really, this 4 would go away because I only have 3 sig figs allowed. And then I still have my times y. Now to solve for y, it's being multiplied. Okay, 0.530 inverse hours is being multiplied by y. To get rid of, to get y by itself, I need to divide, because the multiplication is being done, both sides by 0.530. So now I'm going to divide both sides by 0.530. So 0.159 divided by 0.530 tells me that y is equal to 0.300. And now we got to think about units. When I divide this over, it's going to flip up, and hours will cancel. So we will have moles over liters, which you should expect if you're solving for a concentration. See if you can get these two answers. Put them in your notes for examples C and D. Pause the video if necessary. On to example 4. The decomposition of ammonia on tungsten at 1100 degrees Celsius, 0 order, with a rate constant of 2.5 times 10 to the -4 moles per liter minute. First thing you need to do is write your rate expression. So rate equals K. That's always a given. Remember, we need to write out the word rate. Now, we've got to think about what the formula is. There's not one written. In case you don't remember, that's ammonia. When it says on tungsten, it just means it's used as a catalyst. And we don't even care about the products because we will be focusing only on the reactants in this unit. Okay, so because it says NH3 is 0 order, then we could go through this process if you wanted to see 0. But anything, remember, to the 0 order would be rate equals K times 1, because NH3, ammonia to the 0 order, is going to be 1. So then rate equals K. Let's go on to part B. Oops. Okay, then it says calculate the rate. Got to remind ourselves what the expression is. Rate equals K. Remember that NH3 is not written because it's 0 order, and anything to the 0 order would be 1. So it says calculate the rate when NH3 is 0.075 mole, big M. Remember, that's moles over liters. Well, we have no place to plug that in because it doesn't affect the rate. So then rate equals K, and we know K is this based on the sentence, because remember, rate constant is K. So 2.5 times 10 to the -4 moles over liter minutes. For C. At what concentration mode is the rate equal to the rate constant? Remind ourselves of the expression, rate equals K. So then we would say that all concentrations. Because no matter the concentration, rate equals K. Example 5. All right, the reaction of ICl gas plus 1/2 H2 gas goes to 1/2 I2 gas plus HCl gas is first order in both reactants. Then it gives us some more information. Let's first write the expression. We only need the first sentence to write the expression. So this would be rate equals K, ICl, first order, H2, first order. Again, I'm not going to write ones because we assume if there's nothing there, it's first order. It told us it was first order with respect to both reactants. We don't even need to write these in our expression. We should not. Remember, we have to write the word rate, and we have to write K every time. All right, so it says, what is the value of K? It gives us some more information. It says the rate of the reaction, the rate, different than rate constant, the rate of the reaction is 4.89, so we can say then, following and substituting in, 4.89 times 10 to the -5 moles over liter seconds. Yes, you must show your units. Equals K, which we don't know because it's asking us to solve for K, times the concentration of ICl. It tells us the concentration of ICl is 0.100 moles over liters. Concentration of H2 gas is 0.030 moles over liters. Both of them are first order. So we're going to go through this. Now, remember, as I mentioned before, in a rate expression, we are multiplying and dividing only. Everything is multiplied on the right-hand side, therefore to get rid of it, we have to divide, and on the vice versa. Okay, so we're going to then do this in steps, write as many steps as you need. I'm going to go through this piece with you. I'm going to do it in steps. You can write down all the steps that you would need to help you understand how to do this when you have an example problem. So this is going to go 0.003 moles squared over liter squared. What did I do? I multiplied 0.1 times 0.03. Let me just make sure I did that okay on my calculator, and I did. Use my sig figs. So now to get K by itself, notice that K is multiplied by the 0.003. I'm going to divide both sides by 0.003. So 4.89 to the 5th negative, divide by 0.003. So I get K to be 0.0163. Okay? And when we bring these over, let's talk about the units for just a moment. So we're going to say moles over liter seconds, and then we're going to divide by moles squared over liter squared. Remember that when I do that, it's the same thing as saying moles over liter seconds. When I divide by a fraction, I flip it. Liter squared over mole squared. So this liter cancels with one of those. This mole cancels with one of those moles, and my unit will become liters over mole seconds. Yes, units are important. This value of K, let me circle it, it's kind of gotten lost in here, will be used throughout this reaction for all the next set of pieces. Looking at example 5b. At what concentration of hydrogen is the rate 5.00 times 10 to the negative 4 moles liter seconds and ICl concentration 0.233? All right, so let's look at our expression. Remember, our expression is rate equals K ICl H2. All right, tells us the rate. Don't get rate and rate constant confused. Be careful to plug the right one into the right spot. Rate is different than rate constant. This says rate. That goes up with the word rate. 5.00 times 10 to the negative 4th moles liter seconds equals. Now we're going to go back to and pick up, because I've already forgotten, the rate constant from the previous problem. 0.0163. Liters per mole second. And then we have the concentration of ICl. Remember, square brackets means moles over liters. And we're looking then for the concentration of H2. So carefully plug things in. If you write the expression right above, as I will probably require, not probably am requiring, you need to write your expression above and then plug things in below. You should be able to solve easily. Again, we're multiplying here. We need to get H2 by itself, so I'm going to multiply those and divide them over to get H2 by itself. Let me go through that process with you. 0.0163 times 0.233. So here we have 0.0037 98. I'm not doing a good job of sig figs, but I don't want to spend the time to talk about sig figs right now, so I'm just going to give it 4 sig figs. It really should have 3. And then think about what's going to happen when I multiply those. That's going to end up being the case. And then we don't forget we have the H2 still here. Now, to get H2 by itself further, I'm going to divide both sides. So 5.00 to the 4th negative, divide by 0.003798, and I get my H2 to be 0.132 moles over liters. Let's talk about the units over to the side so you understand how I got the units that I got. So I had moles over liter seconds. I divided by inverse seconds. Remember what that means is that I'm going to take moles over liter seconds. I'm going to flip that. If I have a fraction over a fraction, I flip it. Seconds cancel, and I have moles over liters, which is what we should expect if we're solving for concentration. 5C. At what concentration of iodine chloride is the rate 0.0934 moles liter seconds if the hydrogen concentration is 3 times that of ICl? Again, let's be reminded of our expression. Always write your expression as it will be required, your generic expression, before plugging in. So here's my generic expression. Yes, you've already written it several times, but that's the way this will be required. All right, so right now I see a rate, 0.0934 moles liter seconds. I already have K, 0.0163. Am I remembering that right? Let me check my notes. Yes, liters per mole second. And right now, I have nothing to plug in numerically for either of those two. So it looks like I have an unknown. But the paragraph, the problem, gives us information about a relationship between the two reactants. We will need to use that relationship to solve. So let's look what it says. It says if the concentration, hydrogen concentration is 3 times. So here's what we're thinking about. We're saying that hydrogen's concentration equals 3 times that of ICl. Look at that again. So hydrogen concentration is, that's where I put my equals time, 3 ICl. Just looking at the paragraph here. The sentence. Okay? All right, we are solving for iodine chloride, so therefore we're going to substitute in to only have iodine chloride as our unknown. So now we're going to come here, and where I see H2, instead of putting H2, I'm going to put what H2 equals. Let me show you with my mouse. Instead of leaving 2 unknowns and having H2, I can substitute in what we know H2 to be equal to. H2 we know is equal to 3 ICl, so we're going to plug that in right here. So this becomes 0.0934 moles liter seconds equals 0.0163 liters per mole seconds ICl. And then where I see my H2, my H2, I'm going to plug in 3 ICl. Because we know from here that 1 H2 right here equals 3 ICl. So where I have H2 in my expression, I plugged in what it was equal to. I substituted in 3 ICl. So now, what does that become? That becomes, and now I'm going to erase this. Actually, instead of erasing that, let me move it so that you can still have it to refer to. Sorry about that. I just want to make sure it's there for you to refer to. Okay, so then this will become, and I'm going to do more steps that might be necessary, but I want you to understand where things are coming from. Okay, do you see where I get that from? Note, this 3, everything's being multiplied. I can just rewrite it in a different way. My unknown is ICl and ICl. So I have this. I can multiply the 3 times the 0.0163, divide them over, and then take the square root of both sides. That's what we're going to do. I will do it in steps. 0.0163 times 3. So this side equals 0.0489 liters per mole second times ICl squared. Now I'm going to divide that over. So 0.0934 divided by 0.0489. And I get ICl squared to be 1.91. Take the square root of both sides. And ICl equals, let me take the square root of both sides, 1.38. And I did not put my units in here, so let me do that. I'll go over to the side and talk about units. Let me get a different color for that. So we were originally looking at moles over liter seconds. We divided over liters per mole seconds. So remember what that means. That's going to be moles over liter seconds times mole seconds over liters. So I'm going to flip it. Seconds is the only thing that cancels. Therefore, we have here mole squared over liter squared. When I take the square root, I get moles over liters for my unit. Yes, units will be part of your assessment on these problems. Another opportunity to practice substitution. So in this example, we were given the expression already. The expression is rate equals K, SO2 to the third order, F2 to the first order, and we're given the value of K. So this has already been given to you. Either you calculated, graphed it, or got it in an experiment. Then it asks us at what concentration of fluorine, so fluorine is our unknown, is the rate this, and the sulfur dioxide, concentration is 1/10 that of the fluorine concentration. Let's look and see what we have. Yes, I want you to rewrite the expression. Okay, there's my expression. What do we know? We know we're given the rate. We're given the K right here. Yes, include units because units will be part of your assessment. And then it looks as if we have 2 unknowns. We don't have anything to plug in for SO3 numerically, and we have nothing to plug in for F2 numerically. But it does give us some information about how they're related. It tells us that, right here, the SO2 concentration, the sulfur dioxide concentration, is 1/10 that of the fluorine concentration. So the is your equal sign, and that's how you set this up. So sulfur dioxide is equal sign 1/10 of fluorine. Therefore, I get that expression. Now, we are solving for fluorine, so it should be our unknown. So therefore, wherever I see SO2, I'm going to plug in my substitution. Here's how this will look. 4.13 times 10 to the negative 4th moles liter seconds equals 3.71 times 10 to the negative 6 liters cubed moles cubed seconds. Now, where I see, don't forget it's cubed because it's third order, where I see SO3, I'm going to plug in the substitution piece. And then I'm going to finish my expression. So let me remind you what I'm talking about here. I knew that SO2, apologize if I've said SO3, I keep saying that. SO2 here is to the third order, so where I saw SO2, I plugged in the substitution of 1/10 F23. All right, now we only have one unknown. Let's go through this a little bit further. So, some of this writing is not necessary. Do what you need to do, but you need to get the essence of what the problem is supposed to do. So some of you will need to be in the mindset that I need to write everything down so I can follow how to do this. Now, looking at this part right here, everything inside those parentheses must be cubed because it's to the third order. So that becomes 10 times 10 times 10. So, and then this becomes, and then don't forget you already have F2. So let's talk about this piece right here. Let me actually use my marker. This piece right here that I underline in green is what happened when you took 1/10 and cubed it. So 1/10 cubed, and then F2 cubed. Oops, I apologize. That should be a 3. Let me fix that. I got a little carried away here. This should be a 3. Apologize for that. Please fix. And then F2. So let me go over that again because I had written a 2 on accident. 1/10 is 1/1000th, and F cubed. 1/10 cubed is 1/1000th, and F2 cubed is F2 to the third. So we can take this a step further. 4.13 times 10 to the negative 4th moles liter seconds equals 3.71 times 10 to the negative 6 liters cubed moles cubed. Put that cube back up there, I left it off. Seconds times 1/1000 times F2 to the 4th, right? Because F cubed times F to the 1st is F to the 4th. Now, I still need to get F2 by itself, so I'm going to divide these both over. As a matter of fact, I'm just going to multiply on the right and then bring it over. So let's do 3.71 to the 6th negative divided by, because it's on the bottom, 1,000. And you're going to get 3.71 times 10 to the negative 9th liters cubed moles cubed seconds times F2 to the 4th, still equal to the 4.13 times 10 to the negative 4th moles over liter seconds. As I'm writing this, I'm thinking about some of you may try just to write it all down. If you don't do it with me and then write it down, you will be completely confused when we try to do these on other problems. So please do one of two things. Write it down and listen to me and pause as you need to, or write it down and then go back and listen and understand and follow what we're doing mathematically. So to get F2 by itself, I'm going to divide both sides by 3.71. So 4.13, and that looks a little sloppy. Let me fix that. That's a 4. 4.13 to the 4th negative. Divide by 3.71 to the 9th negative is going to be 1.11 times 10 to the 5th. Now, let's talk about units. I will tell you what the units are, and then I'll show you. So the units are going to be moles to the 4th, liters to the 4th equals F2 to the 4th. Take the fourth root of both sides. If you don't know how to do that in your calculator, I will show you when I return tomorrow. And you should get the concentration of F2 to be 18.3 moles over liters. Let's talk about the units for just a quick moment. So what were our units a moment ago? Our units a moment ago were moles, liters, seconds, divide by liters cubed, moles cubed, seconds. Remember that we're going to flip them. So that means moles cubed seconds is going on top, liters cubed is going on the bottom if I flip it. So then I'm going to have seconds, that's the only thing that cancels, and then it's going to become moles to the fourth, liters to the fourth. And then when I take the fourth root of both sides, I get moles over liters.